Good afternoon, this is Schweitzer, and we're going to do a little video on what we're referring to as the instantaneous speed average. We're picking up here on our smart notes, but really this particular video is going to really be circling around what we're referring to as the position graph. Now the position graph we might refer to as the position time graph, but a lot of times we'll shorten up and just call it the position graph. So we're tracking movement up and down a line. Now, it's on a graph like that's difficult to show, but really we're moving just down a line. It could be something where Hortonville is on one side and we have New London here. And we're just going down Highway 15 and we're going to come back. And that's all we're doing here. So here, this horizontal line is really this line. It is this line right here. So this is our position. So I could really say this is Hortonville right here, and this is New London here, but this is my time. Okay, so we'll leave Hortonville London on there, and it just starts looking at some values here. So this is kind of a graphing exercise. Now you should take a moment and set up a scale and graph this data. Okay. One thing I don't like about this data is it's kind of nitpicky. I don't have a ruler with me here and on this computer, and it's kind of difficult to really get accurate data. Okay. So pause it here, and with your own ruler, you should be able to do something a little bit nicer than I can do. All right. So with that said, time. There's 10 seconds. So I'm going to just kind of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Even if you're not completely, nitpicky every detail, you will get the idea of what we need to know here. Okay, so that's this guy. And then we got total disposition is 7 or 8. So 1, 2, 3, 4, 5, 6, 7, and 8 just off the top. Okay, so this is going to be in miles, and we're sort of automatically setting up that this is positive, up is positive, down is negative, to the right is positive, to less negative. That's our frame of reference. So time, first one is like 0.4. Second, so it'd be like something like here, 0.8, 1.3, all right, 2.1, so the fifth one is 2.5. This is, again, also there's not a huge, because there's small details, small amounts, we're not seeing as drastic change in our graph. Looks straight, but there are some changes there. 6 would be 2.7. All right, so maybe like right there. 8 is going to be 5. So now we got a little bit of a jump here. 1, 2, 3, 4, 5. So, and that would be right here. So the farther I move in a given time, so this one jumped up quite a bit because I traveled more distance, and these guys are relatively small. Okay, so 9 is 6.4, so this is 5, 6, and 6.4 could be like right here, and then 10, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 6.4, and then 10 will just 7.6, something like that. Okay, I may have missed a point there. It doesn't matter. So you'll notice that the line's relatively flat here, and then it shoots up, and then it flattens out again a little bit. So let's just say that's our graph. Maybe yours is a little bit better than mine. Okay, so it's relatively flat. Okay, what it says, how would you graphically determine the average velocity over the first 3 seconds? Okay, so to do this, what you would do is you would, so it says velocity first of all. We're going to add some things in here. Okay, so what is velocity? So velocity is your change in your distance divided by the change in your time. So if you wanted to mathematically calculate this, in the first 3 seconds we traveled from 0 to 1.3. So it could be, change in distance could be the position final minus your position initial. And my position initial is 0, so my net difference here from here to here is just 1.3. My change in time is just 3 seconds. So I could divide those out and I would get my velocity. Now I call it my average velocity because I have 3 seconds. Instantaneous velocity would be literally like 0 seconds. That's might sound strange, but it's a very small piece of time. So, all right, so next it says, how would I graphically do that? Okay, well, what we do here is we do a slope. Okay, so our slope here, anytime, keep in mind, it's dividing the two. So slope, very important, is always when you take your y coordinate, your rise, divided by your run, which is your x. Rise over run. So my rise, in this case, is your position, your change in position. And your run is time. All right. So keep in mind, your slope is, you're always going to be dividing for your slope. This divided by that. And that happens to be velocity. And that is an extremely important factor that we're going to be using for this particular graph. So the slope happens to be your velocity. That's an important thing to realize. And you might note that if you have a flat line, flat slope, okay, that there's no change in position over time. So this would be a 0 slope, would be 0 velocity, okay? And as that slope increases, you get a larger distance traveled in a given time. And it goes steeper. Now I got a larger distance traveled in a given certain amount of time. And of course, if it goes straight up, you travel a distance and have not gone any time, which is called time travel. And we can't do that. Okay? Undefined. So how do I do this graphically? Okay, so we're looking at slope here. So to do it graphically, I'm going to maybe use a line. And all we do is, let's use a different color. Keep it thin. All right, so what I do is I start from my initial point and I draw a line to the time. Now 1, 2, 3. So there I did. Now that's a pretty consistent line here. All I want to do now is find the rise over run of that flat line. So take from that point, this is my distance traveled and my time is 3 seconds. So I'd want to find the slope of this particular line right there. Okay. So let's take a moment and let's just, that's it. And I actually did that in the math already. That's what I did. Get a little thicker here. I want the slope of that line. Okay. And the math in that is actually to the right here. Okay. Right here. That's the math. How would you graphically determine the average velocity over did that? How would you graphically determine the average velocity over from 3 to 7? Okay, that's not so bad. All you got to do is take your line again. Okay. I think we still, okay. Get the orange line again. Let's do red this time. So now the only difference is that I just got to take my line and start the 3. Okay. And 3, 1, 3, 4, 5, 6, 7. Okay, there we go. Now the slope of this line is the one that's going to give us the average velocity over that time frame. So again, I would need to use, this is my run, and this is my rise. And you could do that math very easily. Your change in position would be from 3, your times 3 is 7, and 1.3 to 3.8. So you can subtract it up. Was it like 2.5? Okay, 2.5 divided by your 4 seconds. Okay. All right. Next it says, how would you graphically determine the instantaneous velocity at 9 seconds? Okay. So this is a little tougher here. Okay. So it's like right here. How do I find the slope at that 9 seconds? And to be honest with you, we really, there's two. The main way is this. Okay. They're going to have to give you a little bit more information. Okay. And what they're going to give you on this, because we can't do it without a little more, they're going to give you, typically speaking, what we call a tangent line. And they're going to say that this is a tangent line. And what it means is that this line is the slope at that very dot. Okay. Let's add a page here quickly just to kind of show this. And if I were to have, let's say, a circle, okay, and let's say here's my tangent line, and I want to know, just to give you just an example of this, right there, okay? So it's not exactly what we had, but what's the slope at that very point? Well, this line is that slope at that very microscopic point. So what I do then is this line, it's longer, it's bigger, so we can deal with it. It represents that slope there. So now I can do the rise, and I can do the run of this entire line, and it gives me the total slope at that very point. We call this a tangent line. So you might see something like that, tangent line. So tangent means it connects and has the slope of a single point. And this is used for instantaneous speed or velocity. Okay. All right, so we would need that. Okay. Otherwise, kind of difficult graphically to determine the instantaneous slope or speed at that point. All right, so instantaneous speed. What if you want the, on the side, what if you want the velocity or average velocity for the whole thing? Well, then you would just need to get a line from the start all the way to the end and mark that slope out. All right, so next up. All right, so we're going to start getting a little more into our position time graph. We know our slopes. Now these quizzes, these graphs can sometimes be difficult. Okay, so you can't memorize things, and I really have a hard time memorizing these things because you just can't. Okay, you forget too much. So really, this thing is just a process. And there's a couple things you want to memorize, not, that's very minimal, but you have to walk yourself through it and ask yourself. Position time graph. What does the slope represent? Okay, that's the slope, therefore, all right, remember, slope is when we're going to be dividing. So that's y divided by x. That's position, change in position, divided by change in time. That is velocity. And then you ask yourself, what's a zero velocity look like? It's flat. Okay. Higher it goes, the more velocity I have. Okay. With that, now you're set to think about this problem because they're going to ask you all sorts of things about this. Okay. All right. So it says, what does slope represent? Velocity. Every time I see this graph, I have to look at the markers and make that assessment. what does the area of the curve represent? So we haven't talked about this yet, but so when you do slope, you divide, but when you do area, this is important, it is multiplied. So it's going to be position times time. This would be a meter times seconds. This is a meter divided by seconds. That's my units. You should recognize a meter divided by a second. This is something, if you want to say memorize, go ahead. You need to know that that's a velocity. Meters times seconds doesn't have a whole lot of meaning to us. Doesn't mean anything. A meter a second isn't something we typically would track. Keep in mind, we're just moving up and down a line. Change in position by change in time. So for this particular graph, the slope has a very large significance, but the area of the curve doesn't mean much to us. What changes with respect to positive and negative values? All right, so what's positive, what's negative? Okay, now in this case, position this way is positive, going this way is positive, going this way is negative. Okay, so think about that. Again, all you have to do is think about these things and you get your mind right, then answer the questions. Okay, so that means, now remember, we're just traveling down a line. So traveling towards New London would be positive, if this is New London. Hortonville is right here. Going this way would be negative. Okay. So slope-wise, of course, you should be recognizing from your math classes that this is a positive slope and this is a negative slope. Positive slope, negative slope. Okay. So this is Hortonville right here. This is New London. So we could have a positive slope or I could have a negative slope. Positive slope, negative slope. Very important. What do you notice about this? In a positive slope, we're traveling net in this direction in this amount of time. A negative slope, I'm traveling in this direction. So a positive slope would mean you have a positive velocity, means you're traveling in this direction. A negative velocity means you're traveling in this direction. So here I have a positive velocity, no slope. And this is a positive velocity, positive, positive, positive. Looks like it's starting at some point to tip to zero and down. This is changing. The slope's constantly changing. It's important to realize that as well. So we might note that right from A to B, okay, A to B has a very unique little setup where we have a what's called a constant velocity. Constant, okay, velocity. All right, so the slope here never changes. All right, that means your velocity is never changing. You're not changing velocity, you're holding a constant speed. Here, no speed, no change in distance. Here, it starts out straight, starts out constant until probably d. This is a constant positive velocity, but then it starts to, the slope is approaching flat, so it's getting less and less and less. So we're slowing down, slowing down, slowing down, and maybe we stop right here. Okay, so we're traveling, this slope is steeper than this slope. So between A and B, we're traveling faster than we are between C and D. And then slowing down to a stop. Okay, so lots of little things here that can really mess with you. You got to think it through. If you understand what the slope means, okay, if you understand what the slope means, and you understand what's positive and what's negative and what they mean, even if you forget it and you got to re-rationalize what it means and re-answer that to yourself, you're good to go. Okay. So note this process that you will need to do every time you look at a graph. Memorizing or expecting to be able to memorize every property of a graph is not realistic or fruitful. So you just can't do it. If you jump to a graph and expect it to go right away, you're going to be disappointed. Take a moment, analyze the graph, think about what all the things mean. All right, next one. Okay. What does this, so again, try these questions out. What does the slope represent? Velocity. Again, you should pause this video and try it out yourself. What time frame with the largest has the largest velocity? So again, I kind of talked about it already. Largest velocity probably is the steepest point, which is AB. What is the time frame where the object stopped? Okay. BC. What is the time frame where the object has an acceleration that's positive? Okay, so we haven't talked about acceleration yet. So acceleration you might be somewhat aware of, and this would be where we have a change in velocity. You're accelerating. So acceleration, okay, is a change in velocity. Okay. So in this case, to have a positive change, okay, and we're getting a little bit deeper than we want to right now, but we'll do it. So it's change in velocity divided by change in time. That's a little bit different. Okay. So in this section, there's zero. The acceleration a is 0. Here it's 0. Here it's 0. Acceleration equals 0. There's no change. But here we're slowing down. This is actually a negative acceleration. Okay, so where is it positive? There's nothing where it's positive. We would want an increasing slope. So we want something that goes from flat going more vertical. This would be increasing speed, increasing slope. This would be a positive acceleration. Again, we'll definitely get more into this as we move along, but what is the time frame where the object has an acceleration negative? So this is where we're losing velocity. It looks more like something like we need to go this way, okay, or this way, and that would be in this frame here. Let's say D to F, D to F, slowing down. What is the time frame where the object turns around? Okay, so now keep in mind, okay, this is Hortonville, this is New London. Do we in order to turn around, we need to go from a positive velocity to a negative velocity. Okay, we need to come back towards New London, back towards Hortonville. Okay, and I screwed that up here. This is Hortonville. This is New London. So we got to come back towards this way. And the answer to this question is there's none. Okay, we're not coming back. We just here we're traveling towards New London, doing nothing. Traveling towards New London, towards New London, towards New London, and we slow down. We never come back. And what time frame is the object farthest away? Well, looks like maybe F. I'm assuming this is relatively flat or hasn't turned back yet. So let's just say F. At the end of the object, add a line that shows the object stopping and turning around. Okay, and you can even say going back to Hortonville, and I'll just say stopped. You can flatten it out if you want, and then coming all the way back, and now we're home. Okay, notice positive velocity, negative velocity. So it's really important. How do you turn around all these things? You literally have to go from traveling down a line. All right, so if we're looking at this straight line situation, to turn around, I'm going down, so I got to stop, and I got to go back. Now I can do something like this. So on my graph, I can go positive slope traveling down the line, and then I can go stop, and then I can come back. Okay, this is a turnaround. Now again, I could have done like this, okay, which is fine on the graph, but really this is an instantaneous turnaround. Okay, we were going down the line, we didn't stop, we just turned around. And there's lots of examples like this. I mean, if you drop a ball on the ground, I mean, it turns around pretty fast and comes back up. This turnaround is pretty fast. That might be like this. Okay, this guy right here. Okay, as opposed to something where you drive to Charlie's, stop, eat, and drive home. Okay, so turning around is something that you want to be somewhat cognizant of. Okay, all right. Linear movement. The graph above is simply linear movement. So that's the graph we just did, and therefore can also describe it as a straight line. And I use that straight line a lot to describe it. Using the line below, can you find a way um, to somehow describe the movement of distance? Okay, time got lost on this representation of the movement, so do your best. So again, we can't. Okay, so I mean the distance. I use it a lot. We can go distance here. We can use vectors as we go. Up and down, but it's hard without distance. It's hard to do the actual um, time frame here. Okay. All right. Here we go. All right. So pause this here, and you should be giving it a try. Absolutely. All right. What are the units of velocity? So it's distance divided by time. So it's a meter. It would be meter per second. How is velocity represented in this graph? It's a slope. At what point is the person the farthest away? Now this is a little bit different here. Okay. Person travels. Again, we're just looking at as a line. The person travels down the line, stops, and comes back. And then actually goes, if this is our start point, we could say this is A, this is B, and then position-wise, okay? And then they went to E, well, and then D, they went back here, and then E stayed here, and then F went down this way, F, stayed here to G, and then back, H went back to here. So we're at the same spot at A, D, E, and H. That makes sense? Okay. So at what point is person the farthest away? Well, here, that happened to be, this is the largest distance from here to here. So at what point is this person the farthest to the right? Okay. Again, up and down, right, left. So you could say, if they're saying to the right, would be B, all right, would be this time frame here. If they're saying just net distance farthest away, then it could be F. So to the right, I guess B would be our answer. Okay, this would be right, this would be left. Okay, when the person stop? Stop between D and E. D, the person stopped, D to E, and they all stopped between F and G. F and G. When did this person travel the fastest? And that's speed, velocity. What is that? So now this is a negative velocity. This is a positive velocity. It's not asking about that. Just this is actually referring to a speed. So these are identical. Okay. So EF would be the or GH. What's my average velocity? Okay, now technically average velocity here, take your slope, okay, this is just going to be, all right, there we go, from the start Try to get my as we mentioned, from start to end would be nothing. So my average velocity here is 0. What's my average velocity from A to C? All right. So now that I can do right there. Okay. And there aren't any numbers here, so really it should say graphically. How do I do this? And it says finally make sure you can represent the last two on the graph, and that's what I just did. Okay. All right. Person walks 10 kilometers in 30 minutes at a constant velocity. Calculate the average velocity of the walk. Okay, let's do that quickly here. All right. So, all right. So says 10 kilometers in 30 minutes at a constant velocity. Calculate your average velocity. So, well, think about this. You're doing a constant velocity, so there's no acceleration, or acceleration equals 0. So our line is going to be flat. Okay, no change in slope. Average, so change in distance divided by change in time. Okay, my change in distance is 10. My time is 30. My unit's going to be in kilometers per minute. So this is divided out is just 0.3, 0.3 kilometers per minute. And that is a very legitimate velocity. All right, sketch the graph below. Okay, so how did that work? Okay, well, so position, time. Okay, so at this time, I'm at this location. So I would just, and it's constant, so I'm do the best I can with my pencil and draw a straight line. I could have stopped there. I should have stopped there. Person B walks slow but fast, but slow then fast, but gets to the same point at the same time. What does this look like? All right, so and that's saying about constantness. So let's slow. So let's go slow first. All right, and then speeds up to catch up. It starts running. Okay. Person C runs nearly the whole way, but walks very slow the last bit of distance. So I don't know, let's runs. So it's gonna get there pretty quick, but then just walks. Now I'm almost there. So remember, this is on a line, and we could say that this is point A. Let's say this is point B. So this is A, this is B. So this last person C, this person literally is like right here. Okay? They're only a little left. But spends a good amount of time walking, barely walking. So there you go. Most of the time, this is A person, B person, C person. Most of the time that C spends is walking. Okay. Who has, no, here's the next question. Who has the higher average, I should say, velocity? Take a moment and think about that for a second. All right. We don't want velocity. A, B, or C? Okay. A, B, or C? Who has the higher average velocity? Now again, think about this. What was our method for finding velocity? We take our line, all right, and let's do a different color. Start at the beginning and go to the end. So my line wasn't too straight for A, not too bad. But A is a constant velocity, so A's velocity never changes, so its average is the same as its constant. But A, B, and C, they're all the same. And that's the key thing to realize, that all three have an equal average velocity. Okay. All right. All right. All right. A little bit of math. Now, again, a lot of stuff we're doing your position time graph is just non-mathematical, but let's just do a little bit here. So, mathematics is speed and velocity. So, velocity is position divided by time. Rearrange the equation solving for distance. Okay. So if velocity is equal to distance divided by time, then velocity times time equals distance. Okay. Important to realize. What does the time really mean in this graph? Okay. So the time in this graph, I guess, is referring to the net difference in time, or the average time. Okay, the time that you're spending traveling this distance. Okay, or average time. So velocity is change of time. So rearrange solving for time. Okay, so now time, okay, is equal to distance divided by velocity. So make sure we're starting to look at how we rearrange these things. Now, just algebraically, we have velocity is equal to the change in distance divided by the change in time. As long as we're not having addition subtraction, then things just move diagonally. Okay, that's really important mathematically here. Okay, they just move diagonally across the equal sign. Do not trap the variable you want on the bottom. Okay, bottom is not good as far as it's giving you a reciprocal. So what I did for this guy was I said, okay, I got velocity equals distance divided by time. All right, I could have moved distance down here. This would give me velocity over distance equals time. But the time is still on the bottom, so I had to leave it like this, 1 over time. I don't want that. So the very first thing I do when I solve for time is I want to get time off the bottom. Okay, so I'm going to take the velocity equals distance divided by time. I'm just going to move diagonally. Move this guy up here. All right, that's going to give me velocity time equals distance. And then I want to get time by itself, so I move velocity down here, and I get time equals distance divided by velocity. Okay, and we will be doing lots of this little moving variables around to solve for certain aspects. That's really important. Okay, all right. Thank you very much. I think this is my last slide here. It is. Okay, so take a moment and check out with your just a little bit of math here. And I'm not even sure I'll do this page here. So velocity is change in distance divided by time, and this is just plugging in some stuff and solving out some very initial math stuff. Okay. The car is traveling an average velocity of 25 miles per hour, so that's V. The person travels 45 miles. How long was the person traveling? So we're looking for time here, actually, right? Time. So that's a misnomer word there, but so it'd be, let's just solve for time. So again, I rearrange. So time is distance divided by velocity. So turn it around. The distance is 45. The velocity is 25, and I trust that you can do that math. The next one, a ball is rolling down a 1.25 meter ramp for taking 3 seconds. What's my average velocity? velocity is equal to the change in distance over time. If that time is not a very, 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 very small time, then it's always going to be considered average. So the distance is 1.25 and the average distance over the 3 seconds. I'm assuming you can do this math. The cat runs 5 meters for 3 seconds. How far did the cat run? So we're solving for distance. Velocity equals distance divided by time. Solve for distance. So velocity times time equals distance. Now you're going to find that you might want to do this stuff in your head. But in this class, this sometimes is the only problem. They just want you to rearrange it. So showing your variables, plugging your variables in is very important. 5 times 3 equals 15 meters. Okay. It's also important here to see that this is a meter per second times seconds equals what? The seconds cancel and we have meters. That's what I just did there. So my unit's meters. If a cat is 3 meters away from you and walks 5 seconds at 0.5 meters, how far away is the cat? All right, so you can think of this logically here, but let's just do a little math here. Okay, so velocity is equal to change in distance. So position final minus position initial divided by your change in time. Okay, so position, now we're talking about just moving up and down a line here. And I marked frame of reference, this is 0. So the cat's at 3. And they went to, well, we don't know how far they went. Went down the line someplace here at a rate of 0.5 meters per second. All right, so let's plug the values in. Oh, first let's solve. Okay, now I'm going to solve for position final. Okay, so I could, in this case, divide out, subtract over. This is in parentheses here. All right. So in this case, your velocity is 0.5 and position final is the unknown value, PF, minus 3, and then time is going to be 5 seconds. All right, and you can do the math on that as well. Someone might just put this together and just call it change in distance over time, which is, right, and then the average is, velocity is here. And then they would multiply across velocity times time equals my change in distance. So this is the 0.5, and then time is 5, so half of that is 2.5. So they went from 3 to 5.5. And that's this guy right here. In space below, draw a position time graph representing the motion of D. Okay, so the cat is 3 meters away and walks for 5 seconds. Okay, so let's do this right here. And position time graph. All right, there's that. This is position, this is time. And the cat has a constant velocity, I'm assuming. It would just be a straight line and looks like this. Something like that. Thank you very much.